Well, I hope I have not given you my cold. So I've been the one coughing at the back. And I've had to rethink this talk quite a bit because it was originally meant to be the morning of today, in fact. When I said I would do the Endnote, I decided that I would actually listen to all the talks that had happened beforehand and try and write my talk again as I went along. So there is actually quite a bit of reference to people's talks, which I think is good. For the last year and a half, I was effectively seconded to a project within UK Research and Innovation, which is kind of the new funding umbrella organisation in the UK. And the main part of that was to talk about was to produce the white papers, the infrastructure white papers that Lord Willits referred to yesterday. So I will touch again on those, and I've even managed to swipe the original slide deck as well. So I have the proper headings and everything. So the thing that's been bothering me over the last year and a half, which is kind of one of the reasons I volunteered to kind of produce the roadmap, was the role of computer architecture. So the various bits of hardware that we use and how they are evolving. But not just that, it's what our response to that is. And our response is mainly in terms of the software that we write. Not just the software for the applications, but the software that controls how the hardware works at all those levels. So this is me listening to you all, reflecting back, I hope, asking what do we need to focus on and why. And you can see now from here that, yes, it does work. There's me, Jeremy Yates, Dirac and STFC, with help from an insight from Susan Morell, who led the production of the roadmap, is now retired. The UKRI Infrastructure Expert Group, all those who were on that, can you raise your hands? I can see, yes, see at least 2, 3, okay. And there were 3 others in that group who were here, so it's a very wide group. Obviously Peter, is he gone? Yeah, okay. Paul Kalasia, is he gone? Yeah. Jackie Pallas, I'm afraid, died recently. Stig, who's gone. JISC, the Joint Infrastructure, I forgot what it's called now, but it supplies the UK's NREN, our National Research and Education Network. Hennessy and Patterson, which is a large book that most of us in senior positions in Dirac have got, which talks about a quantitative approach to computing architecture. The Dirac Technical Working Group, which has existed for 9 years, and the new IRIS Technical Working Group, which has existed for a year and a half, and colleagues in UCL Computer Science, so Dennis Tim, UCL RITS, that's Research Infrastructure within UCL, and that's Owen Kenway, who's over there. David Conning from Imperial, who I've worked along with a long time with, Pete Clark, who's the director of IRIS, and Daniela Bauer from Imperial, who I've worked a lot with over the last year and a half setting up IRIS, and Darren Haskins from Mellanox, who I've enjoyed many a conversation with over the role of interconnect. These photos, which Susan picked, show the kind of big range of things that the UK does with its infrastructure. So designing smart cars, culture is big. That's one of the great surprises that came from our roadmap work, was the social sciences and the arts and humanities are now demanding as much resource as the physical sciences and engineering, which is a big change from 3 years ago. There's the traditional UK leadership in biomedicine and health, but also transport, how society works, and things like that as well. So, as Mark said in the opening talk, and I'm going to say in the closing talk, the UKLI roadmap decided to take a sector approach, and it based these on the S3 categories, which structure things as sectors. So there's the biological sciences, health and food, which is led by the biology, biotech, what's the S stand for? Research Council, and the Medical Research Council. The environment, which is led by the Natural Environment Research Council, but also the Met Office have played a big part in that as well. Energy, which is led by the Engineering and Physical Sciences Research Council. Physical Sciences and Engineering, which is led by the by the Science and Technology Facilities Council with help from EPSRC. So you kind of see the odd way we organise physical sciences in the UK reflected there very well, in that it's spread across 2 research councils. And then the Social Sciences, Arts and Humanities, so that's the Economics and Social Research Council and the Arts and Humanities Research Council. And then the really interesting one is that computational and e-infrastructures, which EPSRC led, that's no longer the case, was hyphened off and given its own separate sector. But the role for this sector is that it supports all the others. Okay, if you want to go to that website, you can see how we're getting on with that roadmap. So the whole timeline, this process began February 2018 is when we began to try and do this, produce an infrastructure roadmap for the UK. We'd never done it before. And if we'd realised how much work it would take, I doubt we would have done it, but there we go. So the first thing we did was we actually looked at the data and tried to understand what we were. Then we wrote that up and we reviewed all our inputs. Then we began to think about what we might become and how we would do that. Then we reanalysed ourselves, and then at about this time, we had a really good hard look at what we come up with, and then we're still waiting for the first edition to be published. It was meant to have been published in August. That's probably going to be October, November now. So the roadmap report looks at what infrastructures are, and it defines them as data and computing systems and communication networks and any other tools that are essential to achieve excellence in research and innovation, or R&I as it became known. So we did this landscape analysis. We uncovered lots of things that were infrastructures that had been quietly hiding away, and then we began to do our assessment of future priorities and opportunities. The scope, we came up with 3 kinds of facility. So there are the ones that are go back a bit. There are the ones that are that provide general generic facilities, so IRIS and Dirac and Archer and so on. And these have expert user support and help. Then there's actually the infrastructure associated with other facilities, and that was actually quite important that we identified that. There was a lot of argument about how we ordered these in terms of bullet points, so because people felt they were second class if they were down here, or third class if they were down here. Susan kind of ordered them in the fact that this was the shortest and that was middle and that was the longest, so in terms of title. So, but it was amazing how edgy people got over this. So we had e-infrastructure associated with other facilities, so provide tailored data storage, analysis, throughput computing. So like CERN, so the World Large Hadron Collider Compute Grid is a classic successful example of that. Diamond Light Source is a classic example of that in the UK context. The Square Kilometre Array will be a classic example of that. This also has expert user support and help. The somewhat fuzzy one was e-infrastructure associated with research centres and institutes. These often have in-house e-infrastructure tailored to support their research. So in the UK context, that would be something like Cancer Research UK, Institute of Cancer Research, that very specific one or two buildings, but and the crick, I suppose, and things like that. This may be dependent on access to e-infrastructure facilities for larger scale jobs. So these tend to be smaller and will often be using this or a bigger version in here. This was actually a very powerful definition. It really helped to sort things out. You'll have seen this diagram before. Mark showed it. Claire, who sat over there, she did this diagram. And it kind of shows you the landscape of the UK very well in terms of the main facilities. So there's Jasmine, which Phil runs, there's Iris, there's Elixir, there's Sanger, there's Grid PP, there's the EBI there, there's Expert Tier 2, Archer, Met Office, Dirac, and so on. And around that, you've got about 100,000 academic and industrial users. You've got the Janet network, or JISC, and then you've got these various software infrastructure and projects, the Collaboration Computational Projects, Health Data Research UK, and the Alan Turing Institute. So this is our attempt to visualise what we are. We kind of separate into high-throughput computing, data-intensive computing, and supercomputing. So this is the kind of timeline where we kind of met. So the first big meeting was March in 2018, and we produced 7 white papers: software and skills, industry, supercomputing, which Mark led, networking, which Bob Day led, authentication, authorization, and accounting infrastructure, which Bob Day led. Bob Day's now retired, that's why I keep saying left. Cloud, which Phil led, and data infrastructure, which I led. And then we went through a series of workshops, and then we finally handed them over to UKRI on the 30th of April this year. And I think we were all very glad when that happened. One of the things that came out was the significance of e-infrastructure. We kind of knew it, but it was interesting to measure it. And the increasing digitization of research and expansion into new fields. So the whole social science and arts and humanities, they have been zooming along. And there were a lot of deprecating comments about what they asked for, that they didn't know what they were doing, etc., etc. I kind of ignored it because, having worked with them, I got the impression very quickly that they knew what they were doing. And why they were doing it, and where this demand was coming from. So digitization of collections, this whole culture, which is really important. The sort of knowing where we've come from and who we are and how we interact with each other and things like that are very important. The data are increasing volumes and complexity. Let's say, we often forget that the most complex thing around is us and our interactions with each other. And again, the complexity of data, the data models that you find in social science and arts and humanities make those in physical sciences and engineering look rather simple. That's why they can't build models, because of course the data are too complex. The data are too complex at present, and we can't generate those kind of models to gain insight. And you will see that the infrastructure data element, you can see now that it might not be the primary field, but everyone's kind of doing it. And everyone's agreed what the building blocks are. This was ubiquitous across the patch, and networks, software, application codes, but also the tools and the libraries and things like that. Computers, obviously, although that might not be obvious to some. Data storage was particularly archival storage and preservation, and access mechanisms. How do you use this stuff? How do you lower that barrier to actual people actually using it? So where did the research drivers come from? So the computational requirements of models, I'll stress models there, increased resolution. So Lee talked about that yesterday. So if you have the average PhD or early career researcher modelling program, basically the first thing the supervisor is trying to do is double is to halve the grid size, which in 3D immediately gets you into needing 8 times more resource. If you've got a temporal component, you're up at 16 times. And if you look at some problems, you quickly get up to 32 or 64 times. And that's going every 3 years, okay? Which is super Moore's law by a long way. And I always think that HPC and modelling and simulation is a meat grinder, really is. Because we're not like the experiments where it's kind of fixed and you have some idea of what you're doing for the next 3 years. We kind of don't, which is why modelling and simulation is very hard to actually predict. Increased complexity. So you're putting in new processes. You're kind of understanding new physics. You realise you've approximated or you've missed things out in the past, and you got to the stage where you know what you're calculating is wrong, because you're not just matching the data anymore, and then you've got to go back and put in the real physics. You can't use the subgrid or the heuristic or the what was it, proxy that someone used this morning. You can't use it, right? So you've got to go in there and do it properly, and of course that means your code is 10 times slower, right? So you've got to cope with that. The coupling of models, multi-physics, multi-scale modelling. In my area in particular, we're putting chemistry in to our MHD codes. You've got feedback going on there. But the ultimate goal of all of this is that we want to get into real time. So the solar community in the UK have an ambitious plan to try and model the sun every day. That's quite hard, but it's coming in sight actually. And also the quantification of modelling uncertainty. So you can either do it intra code or use large ensembles of simulations to provide robust statistics. But we've now got to start thinking about how we understand what the errors are in our codes and quantify them. So direct numerical simulation and modelling is obviously what we've always done, but there's a growing requirement for simulations and modelling concurrent with experiments or observations. Data analytics is looking, that's becoming increasingly dependent, and finally AI, which has implications for both hardware and software. Though as Peter showed, I think, very well, it does look a lot like this, fortunately. The other thing that we had to think very hard about was the flows in the research data life cycle. You generate your data, and remember that supercomputers and HPC AI now generate huge amounts of data, so that they're as big as that they're starting to look as big as a big experiment, and there has to be some kind of supported workflow that allows you to reuse the data archive it and other things, and particularly add metadata so other people and other systems can find it and use it. So the research drivers and technologies, these are the sectors: bio, life, environment, energy, physical science, engineering, and social and humanities. These are the kind of things that we're doing, modelling and supercomputing across here increasingly now. Experimental and observation, analysis and networking all across here. Increasingly cohort and longitudinal studies in the environment and biolife, but also now in social. Sensitive and confidential data and how that's governed is now in quite a few areas. And the digitisation of collections, which goes on in bio and life quite a lot, but especially over here. So the kind of wealth, the kind of range of things we're doing is much more than it was 10 years ago. So the kind of schemes that we began to come up with, one of the things that the UKRI strategy really did in the roadmaps is the centrality of software in all its forms. And so one of the things that we want to make sure is that there is access to research software engineer type for new and all communities, quality control support, the need for new software for exascale and AI, co-design program, so as well as working with the IT technology companies, also increasingly working with maths and computer science, and the ubiquitous requirement for training across all career stages, actually. So upskilling and reskilling are just as important as training people in the first place. Better networking, access management tools, and where applicable, using cloud, particularly as a technology. We tend to often say cloud and mean a public cloud provider like AWS. I think very much in our own white paper that Phil led, we thought of it more as a technology that you can use, and that will come across in a moment. Industry, a proper program to allow industry to use all of this stuff. Computing, looking at supercomputing, trying to aim for exascale by 2030. We've actually made that 2025. Sustained investment in research community for facilities and research centres, so we can actually take part in those big experiments. And the creation of a technology foresight and testbed programme. For data infrastructure, actually sustained investment in data centres. I don't mean a data centre, I mean a centre where data is housed, because we're just seeing the load ballooning. And also resources into people, so we can do proper data curation and data management. So why are we doing all of this? I thought I'd show you some pretty pictures. So this is a project that I'm involved with. This is it's still embargoed, actually. I'd forgotten about that. But these are data taken by the Atacama Large Millimeter Array out in Chile, which is run by the European Southern Observatory, which is a treaty organisation of which the UK is a member. And this is mass loss from red giant stars. So these are stars come to the end of their life. They've ballooned up, and they're starting to shed their outer atmospheres. And it was thought that these winds were homogeneous and fairly unstructured, and you can see actually there's a lot going on in them. Okay, and I hope you can see that. You know, they've got these odd spirals and things like that, and they're certainly not spherical winds, which is what we thought they were, and that's how we've been modelling them for the last 25 years. So the data, these are huge data sets compared to what we were used to even 5 years ago. So that they're about 10 to 100 terabytes each. And when we actually get the high resolution data, they will grow to about 500 terabytes. So they will get very, very, very big. The processes that are going on here are non-linear and non-local. So simple approximations are now out, and one of the reasons for that is because the data is so good. We do magnetohydrodynamics, we've got chemistry in there. We have to use materials science because a large amount of the stuff that's coming off is in the solid state in form of aerosols. The transport of photons is very important because the photons actually heat things up, but they also dissociate molecules. How we calibrate the data, we have to have a good understanding of signal processing. This is an interferometer, and also we've got to do image analysis. So one of the things that we've been able to do with this project, which is actually one of the largest grants of time that ALMA have ever given, is to use AL and ML techniques to reduce and process the data. In the olden days, where the olden days were 3 years ago, the calibration would be done by eye. There was simply too much. So we had to train algorithms to actually calibrate the data, spot atmospheric glitches, take out interference and things like that. That was the only way to make this tractable. The other way to make it tractable was when we were reducing the data was to make use of very high RAM workstations to reduce the data. Otherwise, would be, these data would be being reduced in 2 years' time, not in the 3 months time frame that we actually did it. So a combination of better software and better equipment meant that we could do this in the first place. Okay? And we're the only legacy program to actually produce any data so far because we did this. We're also using AL and ML to identify the physical structures. These are so fine, there's so many pixels in here, and when the high resolution data is taken, that it'll be even worse. That actually trying to identify all the physical structures by eye, it would take forever. Okay, so we have to now use these and train AL and ML to actually understand what's going on. And some people would like to use deep learning to actually see if they can extract the physics. And good luck to them, I say. I'm up here, so I'll be using clusters to model and interpret the data. However, right, we can use the same clusters to do the deep learning. I think that's one of the exciting things that we can do. So I think one of the things, of course, that we want to do is compare the outputs. So this is a really interesting computer science problem as well. What I'm trying to get across here is a simple set of data, well, maybe, like this. One of the joys of astrophysics is that we have to span the whole of engineering and physical sciences to do our science. So we're actually quite a good barometer of what's needed very often in those fields because we have to draw on so much stuff. So the challenges we face. So Mark gave me the unenviable task of trying to write down a kind of architectural model for the supercomputing white paper. So after a whole day of scrawling on bits of paper, and it really was the classic bin with lots of paper, just trying to get it done. I eventually came up with this, which looked a lot like my first essay at it. So here are the science and innovation drivers. Removing approximations. We've got data to model. We've got these big grids, so the 3D to 6D, so weather, climate, fusion, and lattice QCD, which is Peters, which is 5D. We've got many more complex simulations to explain big and complex data. So we're doing all these simulations, but also the data modeling. So Paul talked about the DAC. The inspiration for the DAC came from the panic of how do we do that, right? Because we've got these problems, and without the work that Paul and his team have done, it wouldn't have been tractable. Right? That was the important thing. So there's a huge increase in data movement within the computer systems. Okay, and this is what I'm trying to kind of show here is the data movement, and you've got the poor old interconnect the fabric, which very often has low latency and high bandwidth, trying to manage through the slow memory, fast memory, the critical cache onto the processor and back again. It's also doing I/O, so is it sending it to cold storage? Are we getting it curated, or it's just simply doing fast I/O for the computation? And as Stig was showing, we're increasingly doing stuff across the cloud as well. Okay, so that was a really nice talk from Stig. They've done so much work to try and make this work. If you look at what it means for the system architectures, obviously the latency is going down. I keep forgetting to put that arrow on, that the latency is going down, memory bandwidth is going up. But you've got the GPU, CPU power with its cache stuck on top of it, and so we had some really nice talks by Martin and others, just looking at the guts of what they're doing, of these new things. You've got the RAM, then you've got non-volatile memory and SSDs. So Paul talked about SSDs. We've also been playing with the with the memristor stuff as well, trying to work out what it is good for and what it's not good for. I have to say we're finding out what it's not good for, but it is good for stream data actually, which is interesting. So we are finding that out. And then the network interface, what your NIC card is doing, and then you're going out looking to your SSD array, your powerful file system, tape, and so on. So this is me trying to conduct a qualitative representation of the challenge we face, to actually make it kind of tractable, understandable, what it is we're trying to do. Just doing it on a piece of paper. I'm happy to say Hennessy and Patterson didn't come up with this either, so I'm going to volunteer it for the next edition. So, by the way, it's a great book. I mean, Dirac's built on it. I assure you that we've actually plundered that book from, it's really good. Just having this quantitative approach to that. And I've just given away our trade secret. There we go. So I've talked about our architecture. I'm not going to talk about Yates and stuff like that. What I want to talk about is the response to these architectures that we've had talked about over the last few days. So the UKRI, the UK needs a software infrastructure strategy that reflects both the central role played by software in the delivery of research and the diversity of the research code base across the UKRI research community. The diversity, there's an awful lot out there, from Python scripts to some of the big applications like Swift and others, and VASP and LAMPs and all that kind of thing, that have been talked around here. We have to admit to ourselves very early on that most of the research is being done on laptops by the youngsters running Python scripts, and they do amazing things. I have to say, the last 10 years, I have seen a renaissance of interest in coding and use of infrastructure resources that has been heartening and gratifying to see, and it's being driven by the youngsters, okay, which is really good actually. I mean, I have to say. So millennials aren't that bad, honestly. When it comes to interest in coding and stuff, no, they are quite different. A bit better than we Generation Xers actually, which is heartening to see. As Peter said, our codes cannot be these static things anymore. We knew that though. We were told this. I was told this when I was 21 as well. But what did I do? I wrote code that is static. And that's why I've had to have a student rewrite everything to make it 3D, right, over the last 2 years. And able to harness the power of evolving hardware architectures. So poor old Frederick, my student, has had to rewrite my rubbish code, and it was rubbish, and he's written brilliant code. I mean, it vectorizes, it kind of knows what it's on. It can flip between MPI. He's making it able to work on on an array of accelerators. This is quite new to me, let alone anyone else. And this agility is needed because where we will run the code is not always going to be the same place. That's something that has got to change. We've got to get used to that we can't be stuck to the same place. And one of the things that has hit all of us, I think, is it's not just about applications. I mean, Panda's talk and Paul's talk really hammer that home, I think. Supporting accelerators, all that work on MPI Batch 2, and also the kind of networking programming. I mean, Paul didn't call it that, but that's what it is, that they needed to do to create these new cheap SSD arrays that work. Note that word, work, right? Which is good. So, one of the things that we really want to do in the UK, and with international partners, and with the IT technology industry, is we desperately need to create a virtual software ecosystem and community. Peter's talk demonstrated, and this is what got us all into it within DIRAC, and that's why he was our technical director, oddly enough. He was able to design at deep level his systems based upon the operational requirements of his applications. Now, people say that lattice QCD is a fairly simple problem. Well, I suggest you go and read the papers. I really do. It's not. It's just that it's a very difficult physics problem to solve, which is why that they had to do this. The rest of us haven't have to do this yet. We're now hitting the place where we have to do this, because we're hitting that level of complexity of parameter space and space over which you have to integrate the lattice QCD community hit 20 years ago. They are now doing things that amaze me. They are making predictions on Dirac systems of particles that are being found by the LHC. That's amazing. Okay. So one of the things that we kind of need to do is look at the bottom. Try to create a smallish cadre of people who understand how our key applications and libraries actually operate quantitatively on hardware. They might already exist, by the way, but we've got to find them and put them together and know who they are. Why do we have to do this? Well, frankly, if telescopes and accelerators didn't have this, they wouldn't work. Why should we be any different? Why should we just slap code on and hope it works? Obviously, they'll be supported by people who write the software that makes the components actually work. I mean, Frederica's talk was really good. I enjoyed that. And Paul's talk really made this point that it's not just applications, it's also the stuff that makes the stuff work. And as we said, Peter's bashed this into us. You'll see it, and he got it from Hennessy and Patterson. It's data, motion, and movement. It's a key to qualitatively understanding how systems and apps work together. And most of us only need this qualitative understanding, right? And a beef that a lot of my colleagues have heard before is that personally I'd like to see computational-based research degrees, when they write their theses, they describe the equipment and application performance in the same way that I had to do when I did my PhD for how an interferometer works and all that kind of thing. Okay? They can't get away with just saying, I use this supercomputer. We just can't allow that anymore. Cloud. This is something that I kind of got into by accident. Cloud middleware development is needed to support resource sharing and ensure optimal matching of science with supercomputing resources. The great attraction of cloud is the portable workflow, the ability to join resources together via whatever APIs that you're using, and just not being limited by that damnable batch queue. Okay, that's what you can actually have a batch queue within your VM, by the way. I mean, and Stig and Paul both talked about that. They working very well, but it's just the flexibility. You can do more. You can do more complex things. Do better science. You can do new science and research. You can bring different data together in an easier way. That's why it's a great enabling technology. It's talked about far too much as some kind of resource you can go out and use. It's an enabling technology. It should be a key part of the future scientists' kit bag. Continued support for existing development. I hope you like what Stig and others were doing, and you know, it is really good what they're doing. We are keeping an eye on what commercial cloud and community cloud offerings are doing as well. But as has been pointed out, they are rather expensive, and Peter explained it very nicely why they're so expensive. I was rather glad because I told him that. However, we do need to address the low latency requirement. Stig's talk again, but also Andrew Laheath from Cullum, who has done a lot of work in Iris to actually measure the latency of the various systems that are open to people, in terms of packet size. And you can see the clouds here we go. You know, you're not going to go node to node with that, right? So you're not going to scale at all. These are some older HPC systems, and this is a brand new one, and you can see it's brand new. So HPC is that. We saw from Stig's talk, because he's done a similar set of analysis, that a 25 gig Ethernet is actually something like this, and a bare metal OPA system looks a lot like that. Looks a lot like this. If you just watch the green line there. So I know Stig and others, and it's in the literature, the hope that if we can get the RDMA packages installed properly into this lot, we might drag them down to around here as well. And as Paul was saying in his talk, one of the things that a lot of us are interested in is just how far can we push, sorry about that, just how far can we push Ethernet down? So a lot of us are quite interested in the ability to push Ethernet down as far as we can, because it's a cheaper technology. It's actually very well supported as well. So, and you know, so we are quite interested in that. So to start to kind of summarise, you know, we kind of do. There is a great need for physical and virtual architecture communities. There's a nascent one within Dirac, and slowly absorbing Iris into that. Know who is good at what? I mean, I still don't know. We need to find the resources and to support key projects and people, so things don't disappear when the funding ends. We've found co-design projects are a good way of understanding how things work, and also how we work together, and we're really good at creating communities around a particular activity and technology. So John Goodacre's talk, I hope, really made that clear as well. I should have put John's, I would do that. And we've been quietly doing this in Dirac for 7 years from Peter's work, and slowly now it's broadened out, so all of Dirac is involved in this kind of work. We're now moving on into accelerators and cloud technology, and these are now both in progress. So in particular, we're using our placement scheme to actually drive this. And we need but what we really need to do now is address the application understanding. So we've kind of got a good idea of what the kit's doing. What's the application doing? So that's the kind of next thing that we want to do. And again, we'll be using our placements and our RSCs to kind of really understand that. So Mark has asked me to develop the Dirac software strategy. Thank you, Mark. And I look forward to getting your talks and exchanging emails with some of you about our software strategy. And I hope some of you will volunteer to review our new strategy. So final thought. So it has been, you know, we've had a lot of talks about AI. So current AI applications will give me 42. Okay? So I hope you all know the Hitchhiker's Guide to the Galaxy. All right? So anyone who doesn't? Oh, good. So you all know what it means then. Excellent. So, you know, but that's fine, because that's what they're designed to do, right? They give you a number or whatever. But what does that mean? What do we understand by this? How did it get this answer? In what sense is this answer usable? Now, I'm not being facetious here, because we've had some really good UK AI workshops to identify what the UK needs to do next in this. And this is a summary that was written about what the meeting said about the current state of AI. So there was a great talk which showed how you can use AI to develop what I would call a lookup table plus, some kind of model that you can poke, and it gives you an answer that's true for a couple of days. Beyond that, it gets very noisy and you can't use it. But it's much quicker doing that than having to do the whole model again. So where is it valuable and things like that. So that's really good. But what we actually recently have come up with, these workshops identified explainable AI as a requirement for both research and application in the future. So we need to go from deep thought, which gave us 42, to the Earth, which was the computer that was designed to sort out what the question was in terms of system size and design. And if you look at what people are doing, it's basically jumping from laptop to exascale. All I say is let's hope the planning has been dealt with. So thank you for your attention.